Hello, in this lesson we're going to be finding the area inside of polar curves and the arc length of polar curves. And before we jump into looking at polar curves, let's remember how this works in the Cartesian coordinate system. In the Cartesian coordinate system, we know we can find the area under a curve by splitting it up into subintervals and using a Riemann sum, so using rectangles to calculate the area. So I'm just going to draw, a representation of what that Riemann sum might look like. Okay, so the way I'm drawing it here, it looks like a left Riemann sum. And if we want the area under this curve, we know, of course, that we would have infinitely many rectangles and the width of each rectangle would be approaching 0. But you get the idea. So we kind of sweep the area out in this direction as we integrate across our interval. So we're basically, to set up the formula, finding the area of a single rectangle, which would be, of course, the height of the rectangle times the width of the rectangle. And the width of the rectangle is represented by delta x, and the height of that rectangle is just the function f of x at the kth x value. So we'll just say this is the kth x value, and then the height of this rectangle would be f of x sub k, like so. So the area of the rectangle would be f of x sub k delta x, and if we sum all of the rectangles across our interval, and we allow for infinitely many of these subintervals using a limit, which is what we see over here, then we're going to get the exact area under the curve. And we can translate this summation notation, this limit of the summation notation, into definite integral notation. And I've color-coded this to show how that works. So this part of our notation here just becomes that integral symbol. So we're integrating f of x dx. That's how we find the area under a curve in the Cartesian coordinate system. And it's based on the fact that the area of a rectangle is just this change in x times this change in y. But let's think how this might work in the polar coordinate system. Again, we're going to have n subintervals, and to visually represent what's going on here, we're going to make the intervals rather wide, but ultimately we're going to want to make these intervals really, really tiny. So we're going to use a limit to let n approach infinity so that each one of these subintervals is infinitely tiny. And in the polar coordinate system, we would find this area. Let me go back for a moment. In the Cartesian coordinate system, when we found the area of just an individual rectangle, we're just finding this area right here. Area is just the y times the x. But now here in the polar coordinate system, we're not finding the area of a rectangle. We're finding the area of a sector of a circle. So I've shaded what one of these sectors might look like, and it's not really a perfect representation either. So we would have, just like with Riemann sums, you could have a right Riemann sum or a left Riemann sum or a midpoint Riemann sum. Here I'm going to draw my sector using a midpoint value. So we would say that from the pole to this point is the radius of a circle, and then if you can imagine, the circle would look something like that. And so this would be our sector here. And then in my next little section, when I want to find the area of this sector here, I can do something similar. Go to the middle and say, okay, now I'm going to think of that as the radius of a circle. And when you draw the radius of that circle, it would look something like that. And you find the area of that sector. And we can keep going and add up all these areas of all of these sectors as we go. So you can see that just as it is with a Riemann sum, this isn't going to give us a perfect calculation of the area inside of this little region here. Right? Some of our sector is extending beyond the curve, and some of it, like right here, for example, is not being captured. Some of that area is not being covered by the sector. But we can do better if we make these sectors smaller and smaller and smaller. They're going to fit better inside of our curve. And so to get the exact area, we want to make them infinitely tiny so they fit exactly, or they're approaching an exact fit. Now, how do you find the area of a sector? That's the important question then, because with Riemann sums, it's quite simple to find the area of a rectangle. We're just multiplying the width of the rectangle by the height. But how do you find the area of a sector? Well, the area of a sector is given by this formula down here. It's just 1/2 times the radius of the circle squared times the central angle theta. The 1/2 is a constant multiple, and we need a way to express then the radius. But if we go back to the drawing, the radius, right here, the radius was actually terminating on the curve itself. So it is an R value on our polar curve. And our polar curve is written like this, R equals f of theta. Right? It could be R equals sine theta, R equals 2 plus 3 cosine theta. There's lots of ways to write polar equations, but generally our polar equation is in this form of R equals and then some function of theta. So that's what we're going to use as our radius in this formula. So we have the 1/2 constant multiple, then the R value, the radius, is just this f of theta squared, and then we're multiplying by delta theta. So the delta theta is this difference in the angle, right? We can think of this as maybe theta 1 would be this angle right here. That's theta 1. And then theta 2 would be this angle right here, this larger angle, theta 2. So the difference in those two thetas, the theta 2 minus theta 1, we can call that delta theta. And here's the picture of that same region. We're trying to find the area of this region. Here's what it looks like if we make those sectors smaller. So I haven't drawn the actual sectors, but let's just draw a couple. If this is my R value, and I'm just choosing to do a midpoint value here, but we could also do left or right. So it's still not a perfect fit. If we imagine circles with that radius passing through these points, right, they're going to extend outward a little too far on one side and not quite enough on another side. So let's make them even smaller. And we're going to get a picture that looks something like this. So we're doing much better here. Very small error already, even with this finite many sectors. But we're going to use the limit to let the number of sectors approach infinity. In the Cartesian system, when we set up our definite integral, we have a lower limit of integration and an upper limit of integration. It's like in a dx problem, those would be the x values that determine your interval, the x coordinates of the endpoints of your interval. Or in a dy problem, you might be using the y values to set up or to establish your interval. Here, our endpoint values we want to think of as these theta values. So what angle is this where we're starting to capture area? And then here, what angle is this? And that's going to be our lower limit of integration and our upper limit of integration. So maybe I'll call that theta 1, theta 2. And we're going to be sweeping around in this direction, just kind of sweeping around and capturing the area as we go. So the integral is always going to move in that counterclockwise direction. And if I want to capture more of the graph, then instead of here starting at, it kind of looks like pi over 4. I don't remember for certain if I made it pi over 4, but this looks like it might start at theta equals pi over 4 and stop at theta equals pi over 2. but we could widen that interval to get more of the curve. But here we can see if we integrate from 0 to pi, we're going to get all of the shaded area that we see here. So we start at an angle here, theta equals 0. Well, if we integrate from 0 to pi, we start at our angle right here, theta equals 0. And we're just kind of sweeping from the pole outwards. We're sweeping along and capturing the area of the sectors as we go. And where there is no curve, there is not going to be any area, so we don't have to worry about like skipping over any gaps in area. We just swing around in this counterclockwise direction, capturing the area as we go. And this is that same graph, but now on the interval from 0 to 4 pi. So we can make multiple revolutions, find this area all using a single integral. Now there are some overlapping areas here, so we want to make sure that we're interpreting it correctly. Some of these regions are going to get counted twice as we rotate around, all the way around to 2 pi, and then keep going around again all the way to 4 pi. So here's our formula for finding the area inside a polar curve on the theta interval from theta equals alpha to theta equals beta. And it all comes back down to that area of a sector. And the integral is adding up the infinitely many sectors that we have throughout our interval. But this is the formula we want to remember. We're integrating 1/2 r squared d theta. The 1/2 is a constant multiple, so I usually bring that outside of the integral. 1/2, then we integrate on the theta interval, r squared d theta. And the r is just our polar equation. If our polar equation is in the form of r equals something in terms of theta, f of theta, then we just substitute that directly in for the r in this equation. Let's try an example. Here we're asked to find the area of just one petal of this rose curve. We have the equation r equals 3 cosine 3 theta. We're going to start by finding tangent lines at the pole. So in our last lesson, we saw how we can find tangent lines at the pole. First of all, we need to know what theta values are going to take us to the pole. So we set our equation equal to 0. So we'll let 0 equal 3 cosine 3 theta. I can divide both sides by 3, and I'll have cosine 3 theta equals 0. And I know that's going to happen when 3 theta equals, now I'm thinking of all the places where cosine is equal to 0. The cosine of an angle is equal to 0, and that's going to happen at pi over 2 and at 3 pi over 2. And that takes me once around the unit circle, but I can see that I have, my angle is not theta. My angle is 3 theta. So I actually want more than just these two solutions I've listed. I'm going to list a few more. I want 3 individual solutions, like non-duplicate solutions. So we'll go around again. It would be 5 pi over 2, and we can keep going. There are 6 solutions on the interval, 6 solutions for theta here on the interval from 0 to 2 pi, but half of those are just going to be the opposite side of one of the other angles. So I only need 3 distinct ones. If I do one more, and I will just to show you, but if I write one more, it's going to end up being a repeat. So 7 pi over 12. And of course, we could go in the other direction as well. We could say negative pi over 2, negative 3 pi over 2, and so on. I just need 3 distinct ones. And I can tell just by looking at the graph where I start. I'm trying to envision where these tangent lines are. And I can see at the pole, there's going to be a tangent line. Like there's one right here, and then there's going to be one right here, and then there's going to be one right here. Like I'm only expecting 3 tangent lines at the pole, like so. Okay, then solving for theta, we get pi over 6, 3 pi over 6, and 3 pi over 6 is the same as pi over 2, and then 5 pi over 6. The next one will be 7 pi over 6, but 7 pi over 6 is just on the opposite side of the angle pi over 6. So that is a repeat solution. I don't need to list that one. Here are my 3 theta values. So that's going to give me my 3 tangent lines at the pole. Theta equals pi over 6 will be one. Theta equals pi over 2 is another. Theta equals 5 pi over 6 is the third. Then we want to make sure that for these theta values, f prime does not equal 0. And we talked about that in our last lesson. We don't want both f of theta and f prime of theta to equal 0, or we end up with a 0 over 0 situation in our slope. So f prime of theta, I'm just going to take the derivative of 3 cosine 3 theta. So that's 3. The derivative of cosine stuff is negative sine of stuff times the derivative of the stuff. So I need to multiply by another 3 up here. So negative 9 sine 3 theta. That's f prime of theta. And now I could substitute my pi over 6, pi over 2, 5 pi over 6 in individually here and just verify that the f prime of theta will not equal 0. So I think that might be faster than solving this equation. Okay, so at pi over 6, I'd be taking the sine of 3 pi over 6. The sine of 3 pi over 6 is 1 times negative 9 is not 0. So we're good to go with that one. Pi over 2. The sine of 3 times pi over 2 is negative 1 times negative 9 is not 0. So we're good to go there. 5 pi over 6. 5 pi over 6 times 3 is 5 pi over 2, and the sine of 5 pi over 2 is not 0. And when I multiply by negative 9, of course, it's still not 0. So those are all 3 valid solutions there. My tangent lines at the pole, theta equals pi over 6. Theta equals pi over 2, theta equals 5 pi over 6. So that's step 1 in trying to find the area, is finding tangent lines at the pole, because it turns out that's going to help us determine the intervals where we need to set up our integral. So here's our pi over 6, pi over 2. Oh, I don't have the third one drawn. But so how we're using these tangent lines, I'm going to go ahead and draw the third one so we can talk about how we choose our interval. Okay, so we will say this one is the 5 pi over 6. Now looking at this, if I want one petal, then I should be able to just integrate between 2 of these consecutive tangent lines. When we look at a petal, we can think of a petal as starting at the pole. So starting at the pole here, and then looping around, and the petal is complete as soon as I get back to the pole. And so we should be able to get exactly one loop if we just look between 2 consecutive tangent lines at the pole. So I have options here. That means I could integrate from pi over 6 to pi over 2. Or I could integrate from pi over 2 to 5 pi over 6. Or from 5 pi over 6 to 7 pi over 6. Or 7 pi over 6 to 3 pi over 2. Or 3 pi over 2 to 11 pi over 6. Or, but you got to be careful here, you can't go from 11 pi over 6 to pi over 6. Because pi over 6 is a smaller angle than 11 pi over 6. If you say you're going to go from 11 pi over 6 to pi over 6, you are actually going backwards. You're going all the way back around here, which is going to cover lots of petals. You don't want to do that. If you do want to work on this sort of interval right here, then instead of 11 pi over 6, what you would do is go from negative pi over 6 to positive pi over 6. Now, why on earth would you want to go from negative pi over 6 to pi over 6 when you could just go from pi over 6 to pi over 2? So here's my thinking about that. If I go from negative pi over 6 to positive pi over 6, I may be able to use one of our properties of integration that says if you integrate something from negative a to a, and it's an odd function, you're just going to get 0. If it's an even function, so let me just go back in terms of coordinate system, because this is when the last time you've probably seen this property. The property says that this is just equal to 2 times the integral from 0 to a, f of x dx, if f is an even function. So we can use symmetry to help us out here. And if I were trying to make a decision, there's lots of options in terms of what interval you want to use. What I would do would be to start at 0 and then just integrate to pi over 6, knowing that I'm only going to get half of the petal. So let's watch what happens there. We start doing these sectors that go around, and we just get half of the petal. So then I know I just need to multiply my answer by 2. So the area inside of one petal would be 2 times the integral from 0 to pi over 6. And then I'm using my formula for area of a sector, which is the 1/2 times r squared. And here's the r right here. So 3 cosine 3 theta squared d theta. That's our setup. The 1/2 is a constant multiple. It can come out. Gets multiplied by the 2 that's out there. So then I just have the integral from 0 to pi over 6, and I'll go ahead and square the inside here. 9 cosine squared 3 theta d theta. Now the 9 is a constant multiple. It can come out. 9 times the integral from 0 to pi over 6. Cosine squared 3 theta d theta. How do you integrate cosine squared? You power reduce. So the power reducing formula is going to give us 1/2 times 1 plus the cosine, and then you double the angle. Here the angle is 3 theta. You have to double that. So 6 theta d theta. The 1/2 is a constant multiple. It can come out. So 9 over 2, integral 0 to pi over 6, 1 plus cosine 6 theta d theta. And we're ready to integrate that. The integral of 1 with respect to theta is theta. And then for cosine, the derivative of sine is cosine. So this is the sine of 6 theta. Now we have to compensate for the chain rule piece over 6. And we're evaluating from 0 to pi over 6. It's nice when one of your bounds is 0. 0 is easy to substitute into trig equations. Okay, so we sub in our top value, that upper limit of integration, and we get pi over 6 plus the sine of 6 times pi over 6, or sine of pi, which is 0. So that's just 0. Minus, and then we're going to substitute in 0. So we get 0 plus the sine of 0 over 6. The sine of 0 is 0. So we have lots of zeros there. 0, 0, 0. And our final answer then is just 9 pi over 12, which we can reduce. If we divide by 3, this reduces to 3 over 2. So we have 3 pi over 4. 3 pi over 4 as the area of one petal in this rose curve. For our next example, we want to find the area of the region between the inner and outer loops of the limacon r equals 1 minus 2 sine theta. The area in between the inner loop and the outer loop. So that would be this area here. And this graph is symmetric, so we don't necessarily have to use an interval that's going to give us the entire thing. We might be able to get away with just finding half of the area and multiplying by 2 like we did in the last problem. We should start by finding tangent lines at the pole. So just looking at the graph here, if I'm trying to visualize, where does the graph pass through the pole? What would tangent lines look like right there? So it seems to me that there would be a tangent line here on that side, and then also one on this side. So that's what I'm expecting to find when I set r equal to 0 and solve for theta. Let's see what happens. So we want to let 1 minus 2 sine theta equals 0. And that happens when sine theta equals 1/2 and theta equals pi over 6 as one of my solutions. That's quadrant 1. We know sine is also 1/2 in quadrant 2, and that's going to be the 5 pi over 6. And then we can keep going, but this was just a single theta right here. So I'm only expecting 2 solutions on the interval from 0 to 2 pi. If I do list more solutions, there are infinitely many solutions, but if I list any more, they're just going to be repeats. For example, after pi over 6, we can add 2 pi to that. It's just going to be a repeat. When we graph it, the graph is going to look the same. So we have 2 tangent lines at the pole, which is exactly what I was expecting, and they look like they're where I drew them, although I drew mine probably a little bit too big. It looks closer to pi over 4 than pi over 6, but it should have been pi over 6. So maybe a little bit more like this for the tangent lines would be a little bit more accurate there. I was just freehanding it. Okay, now we do want to verify, and hopefully it's true because graphically it looks like I have found the 2 that I'm looking for, but we want to verify that the derivative is not 0 at these values of theta. So we will find the derivative of r, and the derivative of 1 minus 2 sine theta is negative 2 cosine theta. Right, then if we substitute in pi over 6, the cosine of pi over 6 is not 0. The cosine of 5 pi over 6 is not 0. So both of these solutions will work as tangent lines at the pole. The tangent lines are theta equals pi over 6 and theta equals 5 pi over 6. Okay, so here's a better picture of our curve with the tangent lines drawn. And we have to think about how we're going to get the area between the inner loop and the outer loop. So what you see shaded in this graph is not the area that we're looking for. What you see shaded in this graph is just the area of the inner loop. But we're going to need to know the area of the inner loop. When we find the area, let's label some angles here. We know this is our pi over 6. And so on the opposite side, we have 7 pi over 6. This is our 5 pi over 6. And on the opposite side, 11 pi over 6, which we may want to write as negative pi over 6. We'll see how it goes. It's helpful to know whether your r values are positive or negative for these theta values. Like you can't just immediately assume, for example, when theta equals 0 that you're at this point right here. It's very possible that you could be at this point over here if you have negative r values. So we have to be careful, we have to be thoughtful about this when we're choosing our intervals. Typically, I would want to know when theta is 0, what are the coordinates of my point? I want to know where I am on the graph when theta equals 0. I think of that as the starting point of the graph, even though there technically is no starting point because theta could be any positive or negative angle. But when theta is 0, r is equal to 1 minus 2 times the sine of 0. And the sine of 0 is 0, so it's just equal to 1. So we have this point, this r theta, at 1, 0. When the angle is 0, the r value is 1. So that is, in fact, this point right here. When theta equals 0, that's where we are on the graph. How does that help? Well, that gives me the sense that if I were to integrate from 0 to pi over 6, I'm going to be getting this portion of the graph right here. What I'm trying to figure out at the moment is what interval is going to give me the inner loop. The inner loop. So if we think about how this thing is going to graph, it's going to start out like this is the orientation here. And then we never get like a sharp bouncing back at these points. It's a very smooth curve. It continues this way, like so, and goes around this way, and then continues to loop around. It's very smooth. And so when is it that we have the inner loop? Well, thinking about that orientation, I was back at the pole at pi over 6. So it's between pi over 6. Pi over 6 is when I started graphing the inner loop. Let me back up a little bit here. Here theta is 0. Here I get to theta equals pi over 6. That takes me to the pole. And so that's right when the inner loop starts at pi over 6. If I keep going, I'm going to be traveling along the inner loop. So I want to start my interval at pi over 6, and then I want to end as soon as I get back to the pole. When do I get back to the pole? Well, I get back to the pole at 5 pi over 6. So this is actually the interval that's going to give me the inner loop. And that's not obvious because if you just look at the part of the graph drawn between pi over 6 and 5 pi over 6, there's nothing there. There's just empty space up there. So it's not obvious that that's where when we're generating the inner loop. But it is, in fact, when we're generating the inner loop. We just have negative R values. That's why they're not showing up in that region. So I'm going to set up an interval that's going to help me find the area of the inner loop. And it might not be clear to you why I'm trying to find the area of the inner loop at the moment, but we'll get there. So the area of the inner loop. Remember our general setup, we would be integrating 1/2 r squared d theta. That's our general setup. So 1/2, we're going to integrate from theta equals pi over 6 to theta equals 5 pi over 6. R squared. And my R is over here. That's the equation that we started with. That's the R. So 1 minus So 1 minus 2 sine theta, that's my R, squared. Don't forget to square the R, d theta. Now how do we integrate this? Well, you need to FOIL that out or expand. So 1/2 integral from pi over 6 to 5 pi over 6. I'm foiling this out, so I'm going to get 1 minus 4 sine theta plus 4 sine squared theta d theta. One-half integral from pi over 6 to 5 pi over 6. 1 minus 4 sine theta. To integrate sine squared theta, we need to power reduce. So plus 4 times 1/2 times 1 minus the cosine, and then double the angle. The angle is theta. We need to double that, so 2 theta. D theta. Okay? And I'm running out of room, so I'm not going to do an extra simplification step. Let's just go right for the integral. So integrating the 1, we get theta minus 4 cosine theta. The derivative of cosine is negative sign, so that needs to be a plus. Now here the 4 times the 1/2 is 2. The integral of the 1 is theta. The integral of the cosine 2 theta would be sine 2 theta. Derivative of sine is cosine, so my sign is correct, but then we need to divide that by 2 to compensate for chain rule. And we evaluate that from pi over 6 to 5 pi over 6. Equals 1/2. Then we sub in that upper bound, so 5 pi over 6 plus the cosine of 5 pi over 6 is negative root 3 over 2. So 4 times negative root 3 over 2 plus 2 times 5 pi over 6 minus the sine of 5 pi over 12. No, 5 pi over 3, sorry, multiplying by 2. So 5 pi over 3. 5 pi over 3 is quadrant 4. So that is going to be negative root 3 over 2, but then we have to divide that by 2, so that puts another 2 in the denominator. Phew, that's just the upper bound. Okay, that is just my upper bound, minus, and now we have to sub in pi over 6. I'm running out of room, so I am going to just switch over to the calculator here, but you can see how we are finishing this one out. We're subbing in the pi over 6 in for theta, and then we have quite a bit of simplifying to do, just arithmetic there. Okay, so I'm just going to come back up here and use math 9 to compute that integral to finish this one up. And I have that area is 0.5435. Now, this is just the area of the inner loop. This still doesn't answer the question that we were asked. We're trying to find the area between the inner loop and the outer loop. We saw that the inner loop is graphed between pi over 6 to 5 pi over 6. So let's label these again. Here's our pi over 6. Here's our 5 pi over 6. So as we kind of swept around from pi over 6 to 5 pi over 6, we had negative r values. We were actually graphing out this portion of the graph right here, like so. So what happens once we pass 5 pi over 6? Where do we go from there? Well, as soon as you hit 5 pi over 6, and let's say going from 5 pi over 6 to 7 pi over 6, what's happening there? Well, as soon as you pass 5 pi over 6, you're starting to trace out this part of the graph. And moving along like this. And you get to this point here. We need to keep going. We need to go all the way around. We could use the symmetry and only go halfway, but if we want to go all the way around, we need to go beyond 7 pi over 6. We need to keep going beyond 7 pi over 6, beyond here, and right here we're going to be at 11 pi over 6. So we even need to go beyond 11 pi over 6. Okay, so we can go all the way to 2 pi, but 2 pi is just going to take us to this point right here. If I stop at 2 pi, have I captured all of the outer loop? No, I'm still missing a very important piece. I would be missing this piece right here if I stop at 2 pi. So I have to keep going. I have to keep going all the way until I get back to this angle. But is that pi over 6? No, that angle's not pi over 6. I need to go beyond 2 pi and keep going until I hit this point again, which is 2 pi plus pi over 6. So that would be 13 pi over 6. If we trace the graph from 5 pi over 6 to 13 pi over 6, we get the outer loop. Now, I want you to imagine that the inner loop isn't here, that this part of the graph doesn't exist. Okay? Actually, I think I can do that. Okay, so we're going to pretend that the inner loop isn't on the graph at all. It's just not even there. So if we integrate from 5 pi over 6 to 13 pi over 6, 13 pi over 6, what are we going to get? What area are we going to be finding? Well, we would start right here, and when we get to 7 pi over 6, we have found that much area. And then we keep going, we keep swinging around this way, radiating out from the pole, around from the pole. It's always from the pole, radiating outward to get these sectors. And notice by the time I get back around to 13 pi over 6, the area that I've found includes where that inner loop was. It includes that. So that if you were to integrate from 0 to 2 pi, 0 to 2 pi, one full revolution around a circle, you would actually be counting that inner loop twice. You would have it in there twice. Because when you find the outer loop, it includes the area covered by the inner loop. And when you find the inner loop, you're getting that area in there once again. So you really get 2 inner loops when you go from 0 to 2 pi. So what we need to do to answer the question we were asked, and the question we were asked was to just find the area in between the inner loop and the outer loop is we'll just find the area of the outer loop. So the area of the outer loop would be all of this. All of that is the area of the outer loop. We'll find that, and then we just subtract the area of the inner loop, and we'll have what we need. And if we do this in a smart way, we're not going to count that inner loop twice. So the outer loop goes from 5 pi over 6 to 13 pi over 6. If we integrate from 5 pi over 6 to 13 pi over 6, one more time, we get this area right here. So that's everything. Then if we subtract away the inner loop, and the inner loop occurred from pi over 6 to 5 pi over 6, then we're just going to have the area in between. And I won't have counted the inner loop twice because if you notice, our interval really doesn't go from 0 to 2 pi. Okay, so area of the outer loop, 1/2 will integrate from 5 pi over 6 to 13 pi over 6. Radius squared, so 1 minus 2 sine theta squared d theta. And then we have to subtract the area of the inner loop. And that went from pi over 6 to 5 pi over 6. Also the same r squared here. Okay, and let's just calculate that. On our calculator, we can use Math 9 here. And we get our final answer, 8.3377. So 8.338. The next thing we're going to look at is how to find the area between two polar curves. So you might have two polar curves that overlap or intersect, and you could be looking for the area in between the two curves. So let's think about how we find points of intersection. Well, in the Cartesian coordinate system, if we want to find points of intersection, we just set our equations equal to each other and solve. Any solution we get that simultaneously satisfies both of our equations is called a point of intersection. And this works well in the Cartesian system because all of the coordinates are unique. But remember, in the polar coordinate system, there are many, many ways to represent the same point on a polar curve. So it's a little bit trickier. You could have two different coordinates that represent the same point, and so it doesn't look like your equations are equal to each other. It doesn't look like the solution you get simultaneously is satisfying both equations, but as long as they represent the same point on the graph, then you are going to be able to call that a point of intersection. So we have to also make sure when we're working in the polar coordinate system that we check for points at the pole separately, because we know at the pole it's even more complicated. As long as r is 0, theta could be anything. So it's quite possible that you solve one equation and you get an r value of 0 and a theta value of pi over 2. And in another equation, you get an r value of 0 and a theta value of 16 pi over 12. And it's not going to seem like that's a solution to your system, because when you substitute the whatever I said, 16 pi over 12 into the other equation, it doesn't give you 0. But that's okay. As long as both equations pass through the pole, then we say that they intersect at the pole, even if they're passing through the pole for different values of theta. In this next example, we're going to find the area of the region in common to both of these polar curves. So the region in common would be the overlapping area, and that would be inside of both the cardioid and the circle. So this is ultimately the area that we're looking for here. And we can use the symmetry of the graph to help us out here. I'm noticing that, assuming that, here's the angle theta equals 0. If we integrate from 0 all the way to pi, so here's the angle theta equals pi, it looks like we're going to get exactly half of each graph. And so we don't necessarily have to go all the way around the circle. This one, let's try and just find the area using the top half of each one of these functions. Now we're going to need to find the points of intersection. And I can see I've got a point of intersection here and here. And then there's also one at the pole. And remember, points of intersection at the pole can be tricky, so we might have to find those separately. But in general, we've got here that r equals -6 cosine theta, that's our circle, and r equals 2 minus 2 cosine theta, that's our cardioid. So if we want to find points of intersection, we're going to set these equal to each other to see where they have the same r value. So we let -6 cosine theta equal 2 minus 2 cosine theta, and let's solve that equation. So I can add 6 cosine theta to both sides, and I'll get 4 cosine theta plus 2 equals 0. And then cosine theta equals -2 over 4, or -1/2. And so just thinking about unit circle now, where does cosine of an angle equal -1/2? So negative in quadrants 2 and 3, and the reference angle is 60 degrees or pi over 3. So it'd be 2 pi over 3, that's the quadrant 2 angle. And then 4 pi over 3, that's the quadrant 3 angle. And let's see if that kind of matches what we're seeing on our graph over here. So theta equals 2 pi over 3. Yep, 2 pi over 3 is here. And then 4 pi over 3 is down here. So that looks right. And we did not get a solution that would lead us to the pole. But as I said earlier, you have to check for solutions at the pole separately. You just need to know that both equations pass through the pole. Now we can see that visually on the graph, but algebraically, if we need to check, we do that by just letting each equation equal 0 separately and solving. And all we need to know is that there is a solution. The solutions don't have to match. I don't have to get the same theta. I just have to know that each graph passes through the pole, and then we can say there's a point of intersection at the pole. And so certainly here, this equation will have a solution. We know the cosine of theta equals 0 when theta equals pi over 2, and there are others, of course. And then we set the other equation equal to 0, and here we're going to get cosine theta equals -2 divided by -2, or 1. And again, we've got lots of solutions here where cosine theta equals 1. So yes, the pole would be another point of intersection. We'll say theta equals 0. Now we're only going to work with the top half of these curves. We could work with the whole curve, but it's going to be easier if we just work with the top half. We just have to remember in the end to multiply our answer by 2. So again, I had here theta equals 2 pi over 3. We're going to have to do this in parts. So we're going to start by finding, and let me shade again just to be clear what region it is we're trying to find the area for. It's this whole region here, but we're going to have to do this in parts. We can't get this in one single integral. We're going to have to find just the area of this little sliver right here. And that little piece is inside of the circle. It's inside of the circle. And then we can set up a separate integral to get this area for this piece right here. So I can set up an integral to go from pi over 2 to 2 pi over 3. Now, if I use the cardioid equation, the area that I would be finding there, remember we start from the pole and we radiate outward like this. So I would be finding this area if I did that, if I used the cardioid equation and integrated from pi over 2 to 2 pi over 3. That is not what I want. What I want is to integrate the circle. And let me take away some of my shading here so we can really just focus in on what we are looking for. And I'm even going to try and hide my cardioid here. I'm just going to color over it with a white pen. I'm just going to completely take it away. Because remember, at the moment, I am trying to find just this little area right here. So we can accomplish that if we integrate the circle from pi over 2 to 2 pi over 3. Remember, when we integrate, we're sweeping out the area of sectors from the pole. This goes from the pole, and you're just like sweeping around this way as you go, capturing area. And there is no area up here. There's no part of the graph up there, so we're not going to be getting anything as we do that. When we go from pi over 2, which takes us to this point on the circle, to 2 pi over 3, which takes us to this point on the circle, our sectors look like this. And they go outward. And that's going to give us the little area that we need. So we're going to set up an integral to go from pi over 2 to 2 pi over 3, r squared times 1/2 d theta. And let's make sure we use the right r equation. This is the circle, so it's the -6 cosine theta squared d theta. Okay, that's going to give us that little green part right there. Now I'm going to erase some of this and get our cardioid back, because next we want to find the area in this part of our region right here. And that is the area inside of the cardioid. So I'm going to go back to my white pen and try to erase the circle, because it's really hard to ignore part of the graph when you're seeing it right on top of the other one. So I'm just erasing the circle away so we can get a clearer picture of why we're setting up the integral just using the cardioid now. So for this part of it, we want to integrate just the cardioid from 2 pi over 3 to theta equals pi. And it's just from experience that I know that this is going to stop at pi, but it's not a bad idea to double check that you're at this point right here when theta equals pi. And we can check that by letting theta equal pi in the equation for the cardioid. That equation is right here. So when theta is pi, we would have 2 minus 2 times the cosine of pi, and that would be 2 minus 2 times -1, or 4. And so we have the point pi comma 4, which definitely is this point right here. So by integrating from 2 pi over 3 to pi of the cardioid, we start at the pole, and we're drawing our sectors going out like this, and we're swinging them around here until we get to pi, capturing all that area as we go. That's going to give us the yellow part. Okay, then we need to bring back in this other part that we already found over here. I think I had that like shaded in green right there. And when we add those two parts together, we're going to have what we need. So our other integral goes from 2 pi over 3 to pi, and it's the cardioid equation, 2 minus 2 cosine theta squared d theta. So we would add these two integrals together now to get our answer, and we also have to remember then to multiply by 2, because we're really only finding half of the region we're looking for. Okay, that equals 5 over 2 times pi, and then we need to multiply that by 2. So the area equals 2 times 5 pi over 2, or 5 pi. Or once again, a little better picture of our graph with our shaded area. Okay, we're going to finish up by finding a formula for arc length in polar form. Now, we have seen the arc length formula for rectangular equations, and we've seen the arc length formula for parametric equations, but now we're going to develop a formula for polar equations. We know that we can write our polar equations in parametric form using our conversion formulas, x equals r cosine theta and y equals r sine theta. So that would be our first step, is to express x as a function of theta and then y as a function of theta. And then we're going to find dx dt. In this case, the parameter is theta instead of t. So we're just going to make all of these t's thetas. We're just calling the parameter theta here instead of t. So we are going to find dx d theta, and then we're going to find dy d theta so that we can substitute them into this equation. To find dx d theta, we are going to use the product rule here on f of theta cosine theta. And to find dy d theta, we will use the product rule here on f of theta sine theta. Here are those derivatives, and instead of writing f prime of theta, we're just writing dr d theta, so switching back to Leibniz notation here. So now we can make some substitutions. I can substitute this in for the dx d theta, and I can substitute this in for the dy d theta. And before we put it all together, let's just simplify what's going to be inside of the square root. So we want to FOIL this out. And when we FOIL this out, I know it's on two separate lines. It wouldn't all fit on one line, but this is a plus sign right here, not an equal sign. This is a plus. So we've got 1, 2, 3, 4, 5, 6 terms here that are all being added together. This term plus this term can be simplified. You can factor out an r squared, and then the sine squared plus cosine squared equals 1, just leaving us with r squared. This term and this term can be simplified by factoring out dr d theta squared, again leaving behind a cosine squared theta plus sine squared theta, which turns into 1. So then we just have dr d theta squared. And then this term and this term are just opposites, so they cancel out. So we just end up with dr d theta squared plus r squared. So this is what we're going to see underneath the square root. And here is our arc length formula for polar equations. We integrate the square root of r squared plus r prime squared. So here it's written in Leibniz notation, but we could also say r squared plus r prime squared with respect to theta, and we're working on the theta interval. So it's from theta equals alpha to theta equals beta. And that's how we find arc length for polar curves. So for our last example, we're going to find the length of the arc from theta equals 0 to theta equals 2 pi for this cardioid, r equals 2 minus 2 cosine theta. Theta equals 0 to theta equals 2 pi, that's going to take us all the way around the cardioid, exactly one cycle. So remember, our formula is going to be to integrate from 0 to 2 pi the square root of r squared plus dr d theta squared with respect to theta. So we need to find dr d theta. Dr d theta will just be the derivative of this r equation that we have up here. So the derivative of 2 is 0. The derivative of negative 2 cosine theta is negative 2 sine theta. So our arc length, integral 0 to 2 pi, square root 2 minus 2 cosine theta, that's my r, so that needs to be squared, plus negative 2 sine theta squared d theta. Now, if we're going to integrate this by hand, we need to do some more simplifying. We would FOIL out under the root here, so you'd have 4 minus 8 cosine theta plus 4 cosine squared theta, 4 cosine squared theta plus 4 sine squared theta d theta. And then the 4 cosine squared theta plus 4 sine squared theta is just equal to 4. So that simplifies well. 0 to 2 pi, square root 4 plus 4 is 8. So 8 minus 8 cosine theta, we can factor out the 8. 8 minus 8 cosine theta becomes 8 times 1 minus cosine theta. D theta. The square root of 8 is a constant multiple, so we can bring that outside of the integral, and square root of 8 is 2 root 2. Integral 0 to pi, square root 1 minus cosine theta, d theta. Then we have 2 root 2, integral 0 to 2 pi. And we're going to want to multiply, let's see, 1 minus cosine theta. I want to try and create a perfect square here. So I'm going to multiply by 1 plus cosine theta over 1 plus cosine theta. Not sure if this is going to work, but it looks promising because the numerator now is going to be 1 minus cosine squared theta, which I can convert to sine squared theta. And the square root of sine squared theta is going to be the absolute value of sine theta. And then I still have square root of 1 plus cosine theta in the denominator, d theta. But it looks like we can do a u substitution here, and we needed to figure out how to drop the absolute value. To drop the absolute value, we want to exclude the interval where the sine function is going to be negative. So sine is going to be negative. It's going to be positive from 0 to pi. It's going to be negative from pi to 2 pi. So if we just integrate this, and we can see from the graph that we do have symmetry here. I should have just integrated from 0 to pi to begin with and multiplied the answer by 2. But that's kind of what I'm thinking here. We're just going to go from 0 to pi now, and that's quadrants 1 and 2. Sine is positive, so I can drop the absolute value. But then I have to multiply the answer by 2. So that'll give me 4 root 2 integral 0 to pi sine theta over square root 1 plus cosine theta d theta, and now we can do a u substitution. U equals 1 plus cosine theta, du equals negative sine theta d theta. So negative du equals sine theta d theta, and this becomes negative 1 over the square root of u du. And we'll need u-bounds here, or I'll just put alpha beta as placeholders for root 2. And I'm going to multiply this by 2 over 2. So this is just going to become negative 2 root u from alpha to beta. And now let's rewrite everything back in terms of our theta. So 4 root 2. The negative 2 is a constant multiple, so that can come out actually. And it will be negative 8 root 2. The square root of u becomes the square root of 1 plus cosine theta from 0 to pi. Negative 8 root 2 times the cosine of pi is negative 1. Negative 1 plus 1 is 0. Square root of 0 is 0. Minus the cosine of 0 is 1. Plus 1 is 2. So square root of 2. And then when we multiply, we get positive 8 times 2 equals 16. So we have an arc length of exactly 16. Okay, wrapping this up, the critical thinking question for this lesson: how are tangent lines at the pole used to help us find the area of a polar region. That's really key step in setting up these area problems, is finding those tangent lines at the pole. So can you describe in words how you use tangent lines at the pole to help find the area of a polar region? And that wraps up our unit on planar curves. Thanks for watching.